Now, basically, that everyone's had a feed, we can get into the serious business of how do you want to die. and basically, we've talked about the process, the building blocks, the tools, the empowerment, your empowerment, but now how we're going to use them. And because we've got about half an hour, so it's pretty tight. So the issue is, what do we want to really focus on? And we can go into cooling. There's a whole adventure, into cooling. How does this thing get used to cool the planet? But we can also talk about nutritional integrity and then preventative health. That's, again, a bit more detail, but maybe not so many people. Another discussion that we thought might be relevant here is this whole nitrogen economy, ecology, and how do we actually manage the nitrates issue. But basically, because we haven't got time for all of them, may I suggest we just take cooling as the key thing, and then we can perhaps, I'll be here for the next 2 days and stuff, we can sort of kick around on some of these others at another opportunity or in discussions. Is that roughly okay with people?
Yes.
Right. Because basically, when we come to cooling, you see, and again, it's so important, this is Einstein again, stepping outside the box and saying, well, what are we really about? And so we've looked at the whole climate change in the context of that CO2 graph, Keeling, and okay, that's our resource pit for bed springs, that's cool. But really, when we now want to look at cooling, we've got to actually see what is actually going on. And of course, as in nature, we've got this thing called a sun. And of course, we've got a planet here, the third planet in the atmosphere, basically stardust, created 9 planets. The bureaucrats dropped off Pluto, but that's okay, it's still there. And here's the Earth, right? And basically, the sun puts 342 watts per square meter continually, on average, into that Earth's atmosphere. And of course, to have a balanced climate, we need to put 342 watts per square meter out to space again. Otherwise, we would go like Venus into a hyper-heated sort of environment. Right? And of course, we've been doing that really successfully for 4.2 billion years, but nature's got smarter than that. It's also put a greenhouse blanket around the Earth, and that's warmed the Earth 33 degrees centigrade warmer than it would otherwise be. It would be minus 17 degrees on average if we didn't have that natural greenhouse effect. So, pretty clever, pretty clever. But what we've done is we've basically enhanced that blanket, you all know this, and so basically instead of 342 watts going out, basically we now have 339 watts per square meter going out, and an extra 3 watts per square meter being retained in the atmosphere. And this is, in a sense, global warming. Okay? And you say, what's it got to do with CO2? And it's a good question. Hey, good question. Because, as I said, CO2 drives 4% of the heat dynamics of the blue planet. Water vapor drives 95%. We've ignored the elephants because they're too big actually to fit in the room. And we can't model them anyway because they're too independent. Okay? And the way people interpreted Jimmy Carter's brief in 1978 was very narrow to investigate the CO2 greenhouse effect, and they defined it very narrowly so they could do the mathematical modelling because they can't model water. But that's history. The bottom line is, what's 3 watts per square metre? That's basically less than 1% of this heat dynamics, isn't it? I mean, heat coming in, 342 watts, we've got a 3 watts per square metre cooling effect that we've got to say, so it's less than 1%. And the answer is, can we do a 1% variation on this heat balance if we use this force multiplier, 95% water? We've more or less said we've agreed we can't do it with 4% because it'll take 100 to 1,000 years. But hey, can water actually give us that 1%? Okay, it already does 95. So can we modify the Earth's water a little bit, naturally, restore things? And we've already seen in our sponge model, hey, yeah, we manage water, hydrographs, etc. So what can we do? Okay, so that's the sort of systems analysis, but also the opportunity now, how do we do that? before I don't have to rub it all out, let's go. And of course it all starts again with the sponge, right? That's the important thing. It starts with the sponge. Because if you don't have water in your soils, in your sponge, you're cactus, right? You haven't got leverage. But once you've got a sponge, then you've got these things which are called vegetation or trees or whatever you want to call them. And of course there's liquid water here. And of course this transpires, we've already sort of said that, 36% water, but this transpires gas. And a healthy forest, as your forest, beautiful forest, your forest will transpire 40,000 litres per hectare per day of water. But to do that, it's got to turn liquid into gas. And to do that, you need 590 calories per gram. Okay, so you do the maths, 40,000 litres times 1,000 to turn litres into grams times 590, and that's the amount of heat that forest is driving up every day, cooling the surface. Okay, because that heat has to come from that soil surface. So it's enormously powerful. So these trees are naturally air conditioning the planet. I live in Canberra. It was a clapped out, arid, dry, hot, dusty sheep paddock 100 years ago when we got it from New South Wales, as you would, you know. And basically, the first thing, you know, Marion Mahoney, Walter Burley Griffin did, they sort of said, hey, we've got to build an urban forest because otherwise this is uninhabitable. They did that, beautiful urban forest. It's now 12 degrees centigrade cooler on a hot summer's day, 40 degrees day, than the surrounding bare, hard, cold, dry, you know, landscape, 12 degrees. So, hey, this is prodigious in terms of cooling. But more importantly, into this global game, you see globally on average, this takes up 85 watts per square metre, so roughly 24% of that solar, you know, incident solar radiation, right? So this, the Earth's transpiration, evapotranspiration is doing 85 watts per square metre. So effectively, I mean, it's a bit complicated, we're not just doing this, but effectively a 4% increase in transpiration would meet our 1% cooling target. Now, the question is, could we increase transpiration 4%? Bloody oath. No issue, because that's what farmers do, don't they? Increase green. We just had that graph, longevity of green, where we had a 2,000% opportunity given us by just a few bed springs. Okay, so can we cool the planet? Of course we can. But it gets better than that, you see, because once this gas goes up as gas, then it'll basically condense again. We'll get rid of the sun. The sun's important, but we don't. But basically, once that gas goes up, it'll recondense and it'll form humid hazes, right? Haze micro droplets. These are very small droplets, and they basically nucleate on things of dust and dimethyl sulfide and aerosols, right? But in doing so, of course, these guys release this latent heat of vaporization, and basically they release that, but most of it goes up to space as infrared energy because it's a lot thinner upstairs and going back down. So basically, you know, varies 70 to 80% of that heat released up, depending on how high you are in atmospheric conditions, will then re-radiate back out to space. Okay, so powerful cooling thing. But it gets better than that, you see, because if we take about 1 million of these haze microdroplets and we coalesce them, actually this is coalesce them hygroscopically, you know, like you bring them together hygroscopically, we create these suckers, right? And basically they're cloud droplets and they form these fluffy white things. They're not sheep, you know. Well, actually, Aborigines call these sheep. Oh, they're called sheep clouds, right? That's what the jumbuck is in Aboriginal language, because they what are these funny clouds on legs. But anyway, basically here's clouds. And 50% of the planet at any time is covered in clouds. And these clouds are powerful because they reflect sunlight, this incidence 342 watts, directly back out to space. And you know that because if a cloud comes over, you have to put on a jumper or a jumbuck, you know, woolly sheep to keep yourself warm. Okay, so basically they do 120 watts per square metre, or you know, roughly 33% of the incident solar radiation. So a 2% increase in cloudiness, 2 to 3% increase in cloudiness will again very much do that. Okay, so nature, again, this is one of these things that nature does. It's just so beautiful because, hey, here is sponge, liquid. She built the sponge. She's got liquid water in the soil. She can actually transpire, cool it, make clouds, cool it some more. And we've already got, see what it's 33 plus 24, we've already got 60% roughly of the global heat dynamics covered in these processes. There's another process that's actually really profound, right? Really profound, and again, we're fully in control on the farm. If we've got a lot of, let's go landscape, and we've got lots of green, it doesn't have to be a forest, it can be grassland with grazing herbivores, etc., etc. And of course that's transpiring, cooling, that's also reflecting some incident solar radiation from the sun. And it's also insulating or protecting that surface. And so this soil rarely gets above 20 degrees centigrade, right? Rarely gets above 20, you know, you measure that. By contrast, if you've got, you know, the sun out here, and basically it's sort of beating down on bare, exposed, dry land, it's basically heating up, right? It's absorbing massive amounts of heat. That soil, right? And that soil, central Queensland, we measure it 70 degrees centigrade. You can't walk on it, of course. It is really hot, no question. But this is when it gets ugly, right? Because basically things, you heat something up and it doesn't just stay hot, it re-radiates heat back again. You know, you heat something up, it's hot to touch, it's re-radiating, right? And so this thing will re-radiate heat back out where it's coming in as shortwave solar radiation, it's going out as long wave infrared re-radiation, right? But it'll re-radiate massive amounts of heat back out. And this is simple physics, you can't escape it, it's Stephen Boltzmann, black body radiators, right? And there's an equation for black body radiation. The amount of re-radiation is proportional to a constant times the fourth power of the temperature in degrees Kelvin. Forget that, got me good? But the point that we really matters is fourth power of the temperature. Because that means temperature times temperature times temperature times temperature in mathematics. Okay, and if you've got a difference in temperatures between that and that, then the amount of re-radiation going up from these systems is enormous. Enormous. And here's a punchline. Basically, the greenhouse effect is proportional to the amount of re-radiation times the percentage absorbed by gases. Okay, and of course the gases are water vapor, 80%, CO2, 12%, 11%, and methane and nitrous oxide, 9%. Okay? But the guts of the game is not the gases, it's the amount of re-radiation. Okay? I mean, look at the equation. And you're in control of the amount of re-radiation. It is you who control whether that stove, that Earth, this Earth, our planet, is on ultra high or simmer. You can turn down the greenhouse effect, not what, I mean, you can change these if you like marginally, but the real guts of the game is you control re-radiation. Stephen Boltzmann physics. And you can do that by just keeping your landscape cool and green. Now we saw in our hydrograph, we can have longevity of green growth. 365 days of the year. That's what nature did, didn't she? She just basically covered this planet with vegetation and cooled it. Created the ice ages. Okay? So it's really that power of us within days. You know, how many days does it take to grow a green cover crop over bare soil? Okay? Within days, we turn down radiation, and we can cool the planet, we can rebuild the sponge, we can rebuild these latent heat fluxes to do this cooling. That will naturally, depending if we've got coalescing precipitation nuclei here, but that's another story, create clouds which will do it further. So what I'm saying is, yes, we can naturally, safely cool the planet, literally in, don't beat yourself up in days, give yourself weeks. Okay, but it's not the thousands of years it takes to draw down CO2. Okay, and then we come back to the discussion, you see, hey, here you are farmers, these are externalities, hey farmers, you're out of business, you know, they can make artificial protein meat and you're on the scrap heap. Hang on, you're running the ecosystem services of this planet through your land management. All you haven't done is written out invoices to send to the stakeholders. Come on, what are the services you're delivering? Air, water, food, stability, social stability. You know, you're the guys that are actually underpinning. You know, Phyllis mentioned it. It's the ecology of this planet that underpins economies and social stability. And you're underpinning that ecology. And here we are, you're underpinning that ecology. Okay, so don't devalue yourself. I mean, you don't necessarily get these guys to pay your invoices because they'll be so high. The values that you're creating are so monstrously high, they haven't got enough loot. And printing more quantitative easing doesn't sort of serve your purpose either. Okay? But the point is that here is, in a sense, your point of agency on this planet. You can naturally cool the planet. We can naturally cool the planet. We must do this. We do this through rebuilding, regenerating the Earth's soil carbon sponge. It's all about bed springs and hydrology. Hey, we did that in 15 minutes. That's fantastic. Well, look, let's ask some questions. If you've got any questions about hydrological cooling, a mucker mystery, and then we can go that. But then I've got another 10 minutes, and we might be able to talk about, if you like, nitrates or something. Right, go up the back.
Can you wave and I'll bring a...
Yeah, wave and he'll get the phone to you. Microphone to you.
Walter, could you talk about like the 50% of rainfall generated by bacteria?
Okay. Yeah, look. Good. No, absolutely important. Now, very important, and see what I'm saying, it's like a jungle, and you're going through the jungle, you see, and it gets always more and more interesting. You say, hey, look at that, it's a log, and then you find out it's a saltwater crocodile. But the point is, the key thing is that you're observing and you survive, right? So go for it. Now, okay, back here we had a cloud. Okay, this is a story here. We have hazes, right? And actually these hazes aren't good because they do warm the planet. So there's actually a warming effect if the hazes are there. And again, that's what's happened now. We're getting a lot of persistent humid hazes. And actually they're both warming the planet, regions, but they're also preventing rainfall. Because while the moisture's up there, it's actually not raining. They're far too small, they're negatively charged, dispersed, and so they don't precipitate. And so there's literally, I mean, actually this is an important point, there's literally up to 5% by weight of water in the air while these humid hazes are flying across all the world's land surfaces, including all the deserts, but they're not precipitating. That's why they're deserts, right? But what we have to do is we say, okay, well, how does nature precipitate these suckers? Well, they are suckers because, as I said, you need 1 million of them. And we talked about this term hygroscopicity. Okay, and again, very, very simple, hygroscopicity. And basically that's just suction, you know, there's a suction in. And basically for hazes to form clouds, and then for clouds to form raindrops, keep going, and form raindrops, you need precipitation nuclei. You need nuclei that have got higher hygroscopicity, that can overcome these negative charges and coalesce a million of these into a cloud droplet and then another 1,000 into a raindrop. And in nature there's three materials that actually do that. The first, of course, are ice crystals, and you know when you have a scotch, then water will coalesce on the outside of the glass, and they're hygroscopic, and they're very important high latitudes, as you go up high altitudes and cold fronts, right? So a lot of our rain, 20% of the rain comes from these basic ice crystals. The other one that we use, of course, is salts. Salt shakers, sodium chloride will absorb water, it's hygroscopic, and of course most of the ocean clouds are formed from salt spray and salt crystals in the air. They're quite distinctive little clouds, they're quite beautiful. But by far the most important one, and we did this in Cyro in our cloud seeding work back in the 60s and 70s, by far the most important one for inland areas, tropical areas, basically are bacteria, hygroscopic bacteria. And these were discovered and identified by Louis Pasteur back in 1870, and he called them Aerobacter orogenes, which in Greek means orogenes, I don't know what they're doing there. Well, he's a scientist, he does it and he calls it as he sees it. But the point is that these things are extremely hygroscopic, and they're in a sense responsible for nucleating about half our rainfall. And then we ask the question where they produced. Now, there's details here that we don't know because nobody's ever looked at the aerobiology and hydrological dynamics of this planet on these terms. We have all this evidence, bits of it, but basically don't have all the details of the full picture. But basically the message is, and we know that the radiocarbon labeling and stuff in the Amazon, that basically 50% of the Amazon's rainfall, plus over 50%, is driven by bacteria being produced in the stomatal cavities of the leaves of these forest trees and going up in the transpiration stream. And of course at 4:30, they've got a little clock on them, and then at 4:30 every afternoon, down it comes again, rain. And so basically we've got absolutely proof, there's no question about it, every day it's these hygroscopic microbial precipitation nuclei that are actually creating that rainfall cycle. Okay? And they're produced by the thing. So we've got the situation that trees don't just need rain, rain needs trees. But that blows the meteorologist's mind, right? Because they're the physicists, they're like the economists, they've got it all worked out. And here's now this proposition that nature drives rain biologically. Profound. Ridiculous. Okay, but that's the reality. Okay, so these hygroscopic precipitation nuclei, and they drive about 50% of the world's rainfall to our knowledge. The question now is, what level of green cover do we need to regenerate those rainfalls? Actually, this is important. Thank you for bringing it up. There's another thing that's very important, because if we look at this system...
But Walter, can I just a clarification here? So if we're going to re-establish this good hydrology around the world, we need trees. Do grasslands do that to any extent?
But no, good question, and that's exactly that. We've got this hard evidence, but this is exactly the story. We're putting this story, this is forensic science. No, because if we take an island like New Zealand, and if we clear 80% of its forests, we crash its rainfall. We know that. We've done that many times throughout colonisation, right? Madeira, Ascension Island, St Helena, put goats on them, or we logged them, right? Killed the forest, crashed the forest, and turned them into scrub cactus wastelands, right? And no longer having the rainfall. The Atlantic Ocean hasn't changed, but certainly the vegetation has. Actually, there's a dude called Charles Darwin. He was here in 1834, and he then basically did an experiment with Hooker, the president of the Royal Society, about 1870. And on Ascension Island, they completely bared the island, and he said that's pretty irresponsible. So they had 2 mountains and basically said, look, can we revegetate one of these mountains to see if, do an experiment exactly on this, because they read Louis Pasteur's stuff. And basically they sort of revegetated a mountain they call Green Mountain and left the other one as Bare Mountain, right? As you would, besides. And now, 120 years later, yeah, Green Mountain gets 25% more rain reliably than Bare Mountain, which is only 5 kilometres because Ascension Island isn't that big. The only trouble is they used some exotic species and had a lot of arguments with some of the Greens in the UK because they wanted to clear Green Mountain because it had exotic species, right? But they won that, so it's still there, don't worry.
Just one more clarification on that. So we can cool the planet to a certain extent by getting green covers everywhere with grasslands, but ultimately we've got to reforest to get the hydrology cycle.
And this is, we don't have that answer yet. We don't know whether it's a shelter wood, an agroforest, what sort of level of trees do we need? No, we don't know what species of trees, what age of trees, etc., etc. We just know where we've killed these forests, we've lost this, but we've got about a dozen case studies around the world where we have reforested and have increased rainfall as a consequence.
But do we have studies that dispute or negate the potential for grasslands doing that? Have we eliminated grasslands?
No, well, we get.
Bacteria that do the
Philip,
same
very good.
thing?
No, we don't have the evidence to eliminate that, but quite frankly, that's hubris. You see, if we think we've got proof that we can eliminate it, we've got to keep our minds open to wonder always.
Are all trees equal in
No,
relationship?
no, all trees aren't equal, right? So this is, again, very profound. You see, not all trees are equal because when we put back a Pinus radiata or Eucalypt pulpwood plantation, we don't get the effect. We've got the Monero, region just south of where I live, where we've cut down a wet sclerophyll forest, coastal forest for wood chips, very progressive. Why are you laughing? It's money. Okay, where we cut down a wet sclerophyll forest and we replaced it with a regrowth pulp forest, but the Monero plateau has lost 50% of its rainfall. These are the mists and the fogs that used to daily, give 50% of that rainfall on the plateau. They're no longer there because we've changed not even the species, the same species, but it's a whole different forest physiology, right? So now there's more sophisticated, and this is why I'm saying to Phyllis, we can never say never because we can always be in wonder. Okay, but I wanted to make this other point here. See, and this comes back to rainfall, very important because I was in India in November with the UN and we were looking at some very innovative farming systems. But the point is when we've got this this re-radiation of infrared heat, we also create basically high pressure heat domes, right? So all this heat going up will create a high pressure heat dome. And this will of course extend over the whole vast region, a continent, the Sahara, Central Australia. And it's just heat going up, creating this high pressure heat dome. And of course, simple physics again, there's no way that moist, cool, low pressure air can muscle out a high pressure heat dome. It goes the other way. High pressure heat domes flow into low pressure. And so basically we can define and guarantee the desertification of regions by clearing them and heating them. Because we will create these high pressure heat domes. So now in India, the challenge is, well, India's still got a monsoon because it's got the Himalayas. Australia had a monsoon. Central Australia 6,000 years ago was moist, wet, savanna forest. Lake Eyre was a 25-metre deep freshwater lake. Freshwater mussels dated around the sand dunes around it. But we lost our monsoon because of this. And now the question is, how at risk is the Indian monsoon if they also do this? You see? And so we humans now are talking about, hey, we have a desiccation and ridification effect at a planetary scale through this land management, these high pressure heat domes, which can be actually quite profound. But again, we don't have all the details and answers and numbers and prescriptions.
Do you buy carbon offsets when you fly?
Do I look up? No. I flap my arms. But no, look, okay, carbon offsets. See, okay, and this is important, so important. Okay, see, we've talked about carbon as part of the natural ecosystem. We said, hey, if we put 3% into bed springs, soil carbon, we can build sponges, and these are the force multipliers that we can use. And yet we then go into economics and politics where we say, okay, we need a carbon accounting system, and we end up with completely fallacious numbers and incentives and what have you. And as I tried to show in that Keeling curve, just drawing down 20 billion tonnes of carbon and having that on some stock exchange or selling derivatives on that, it's just a Ponzi scheme that's costing taxpayers money. And really, we've got to, farmers, this is critical, we've got to say, what's matter? What does matter? Where's life really hinging on? And it's these natural hydrological, natural ecological processes, and how do we restore those? But we always get sucked into these Ponzi schemes.
Walter, I just want to go back to that rainfall thing.
Yeah.
There's the Wairarapa Bush, the bush province in Wairarapa is about 100k by 100 acres. So 1,000 square kilometres.
Yeah.
It was cleared.
Yeah.
And I knew farmers that are dead now, who were born in the 20s and whatever, who said that as it was cleared, the rainfall, the records of the farmers right through the areas of Weaver, Wyoming, places like that, the rainfall had dropped. And, and then you got to a drought, you got a flood drought situation that also... I did forestry science, and they taught us that that sort of rainfall, that I'm not sure what's it called, the rainfall that goes up.
In the small water cycle, it's a
rainfall. Well, we were taught that it was, we had orographic rainfall in New Zealand and frontal rainfall, and the process of the tropical forest system didn't apply. And I used to say, well, hang on, I've got anecdotes from people that I know and trust deeply who just And so I was up against one science saying bollocks. And another, and he was local knowledge. Local knowledge, very much trusted local knowledge. I'm saying, no, drop.
And I'm back, look, the evidence is the evidence. You've got a dead body, it's smelling, you've got a gun, you haven't got a video of shooting it, there's fingerprints on the gun, you work on the evidence, right? On the ground. And so, absolutely.
Well, I was told...
No, okay, you're right.
I was told it wasn't evidence.
No, but hang on, of course, but there are people protecting their backsides and their egos and their position in academia, right? But look, it's very simple, very simple. Basically, the rainfall in the Amazon basin is 5 to 7 times the water flowing out of the basin. Okay? Because every day, as it flows from east to west, it's cycling as that water moves across to the Andes, right? So it's got 5 to 7 times the rainfall in the basin compared to the volume of water coming in from the Atlantic. So there you are. It's the forests that are driving 80% of that rainfall in that basin. Case dismissed.